Hello, my name is Sankalp Sharma. I'm going to present on the topic wavelet transform in signal processing. I'm going to relate it to Fourier series expansions, which we have been taught in class. Uh, so let's proceed. So now we can get the basic idea about wavelet transformation. But first, we need to know about wavelets. So wavelets are small waves which have their energies concentrated in time. Plus, the wavelets can be localized in both time and frequency domains, unlike the signals that we get after Fourier transform. Also, the wavelet transform can be used to get multi-resolutional analysis of a signal. We also know that the Fourier series can be done on stationary time signals, but this wavelet transform can be done in both stationary and non-stationary time signals. This can be considered as an advantage. Now let's proceed to the properties of wavelet transform. Now there are two basic properties of wavelet transform. First is the scaling property and second is the location property or the shifting property. These properties are the same as those which we heard in Fourier transform properties. Uh, the scaling property helps us to adjust the wavelet frequency by multiplying a scalar, which is known as the scaling factor. In location property, or the shifting property allows us to shift the wavelet in time and frequency domains. We need to note that in wavelet transform we can shift the wavelet in both time and frequency domains. However, in Fourier transform we were only able to do this in time domain. We get an extra dimension in wavelet transform to analyze our input signal. Now we can come to the mathematical expression for wavelet transform. It can be represented as follows. The Wik is the wavelet transform which we get. Expression is similar to Fourier transform expression, but we can see that wavelet transform is represented in two independent variables. The first one is I, which is the scale parameter, and the second one is K, which is the location parameter or the shifting parameter. On the right hand side, we can see there is xt, which is the input signal which we are inputting to the wavelet transform, and psi ik is the mother wavelet, and star represents the conjugate of the mother wavelet. Now we are going to look at the difference between Fourier transform and wavelet transform. First of all, we can look at the mathematical expression of both the transforms. We see the similarities in these expressions as well. For example, in both the transforms, the input signal is being multiplied to a term consisting of the frequency of the signal. But there is a major difference in both the transforms. In the mathematical expression of Fourier transform, we see that it is only transforming it into the time frequency domain. However, in wavelet transform, uh, the expression consists of both time and frequency domains. Also, the Fourier transform is applicable only for stationary time signals. However, the wavelet transform is applicable for both stationary and non-stationary time signals. This helps us to get the transforms and signal analysis of the signals which are not localized through wavelet transforms. The third point is related to the second point. In Fourier transform, we get zero time resolution, which means that we get no hint of that relation of the signal with time, but we get very high frequency resolution. So this depends on our use. If we need only frequency domain analysis, then Fourier transform is the thing to go. But in wavelet transform, it has very high time resolution as well as very high frequency resolution. So if we want both the domains to be analyzed properly, then we need to go to wavelet transform. As discussed earlier, the Fourier transform provides us two-dimensional analysis of the signal. In this two-dimensional information, we get the signal frequency and amplitude of the signal after transform. In wavelet transformation, we get three-dimensional analysis, which is better than Fourier transform. In these three dimensions, we get the signal of the signal time and frequency and amplitude. These three dimensions can be analyzed simultaneously if we transform the signal into a wavelet. So first we are going to look at continuous time wavelet transform. Here we apply wavelet transform on a continuous time signal. A continuous time signal is the one in which the independent variable, that is time, is continuous. Continuous time wavelet transforms are characterized by their uninterrupted nature, which makes it easier for signal analysis and hence they are preferred. Now we are going to look at the mathematical expression of the continuous time wavelet transform. We see some similarities with Fourier transform here as well. FAB is the wavelet transform, where A and B are the scaling and shifting factors. Ft is the input signal and omega is the frequency. We see clearly that A and B play a very important role in the time shifting and time scaling properties of the wavelet transform. Just like Fourier transform, we here also we have a reverse wavelet transform, which can be represented in this formula. We get our signal back in time domain and we integrate the wavelet transform in A and B domains. This shows the reversible nature of wavelet transform. Uh, we can see from the uh, mathematical expression of the wavelet transform that B is very vital for changing the width of the transform. This represents how the wavelet transform is going to be represented in the domain we are transforming it into. Hence, B plays a vital role here. Now, the second type of this wavelet transform is the discrete time wavelet transform. This should not be viewed as the wavelet transform of a discrete time signal, but it should be viewed as the discretization of continuous time wavelet transform. Uh, the discretization is done through sampling process. We need to perform critical sampling so as to get the desired results in discretization. This critical sampling ensures that the information from the continuous time wavelet transform is preserved while uh, transforming it to discrete time wavelet transform. This highlights the relationship between the frequencies of original signal and the sampling frequency. So as to achieve this critical sampling, we need to alter the shifting and scaling coefficients as written in the text. We change a to 2 power minus j and b to k into 2 power minus j, where j is the scaling constant and k is the shifting constant. This change in the shifting constants helps us in multi-resolutional analysis of the signal. Now we can achieve the mathematical expression for discrete time wavelet transform just by substituting the values of A and B in the continuous time wavelet transform. At the end, we get this expression, which is for the discrete time signal, and psi is the mother wavelet. Now let's move on to the application and advantages of wavelet transform in real life. So there are various applications of wavelets. These applications present the need to perform wavelet transform at various points in life. First is the data compression. This consists of signal compression, image compression, audio compression, and much more. For example, we sometimes need to compress our PDFs in which we do our assignments. Wavelet transform helps in the compression of those PDFs as well. Second comes the climate analysis. Researchers get multiple scales to research on by using wavelet transform. These scales help in performing the analysis of climate in both short-term basis and long-term basis. We can also use wavelet transform in medical uh, operations such as heart monitoring. Uh, Doctors monitor the heart using wavelet transforms. Since wavelet transform denoises the signal components, this helps in much more cleaner waves for the machine to monitor. And this wavelet transform helps to analyze the signal received from the heart to be diagnosed at different scales. Fourth comes the seismic detection. The wavelet transform decomposes the data into different frequency components. These frequency components make it easier to detect and separate some features like earthquakes. This helps in earthquake detection and the uh, amplitude of the earthquake. The most modernized use of wavelet transformation is in computer graphics. Uh, this mainly consists of texture analysis of photographs and multi-resolutional modeling of various images. In programming point of view, fast wavelet transform has a time complexity of O of n, whereas fast Fourier transform has time complexity of O of n log n. So while handling large data sets, we should prefer to use wavelet transforms so as to make it more quick. So now let's come to advantages of wavelet transform. Firstly, it provides obviously a way to analyze waveforms in both time and frequency domains. And wavelet transform is computationally very fast with respect to different transforms, including Fourier transform. Now, this has been discussed earlier multiple times, but again, wavelet transform helps in multi-resolutional analysis through a wide range of resolutions. And wavelet transform can be applied to both stationary and non-stationary time signals, unlike the Fourier transform. Now, let's see a few disadvantages of the wavelet transform. We are going to discuss two disadvantages of wavelet transform. First is that wavelet transform is shift sensitive. This means that wavelets lack translational invariance, which actually is a property of Fourier transform. In Fourier transform, the signal which gets transformed uh, after transformation, it is not shift sensitive, but a wavelet is shift sensitive. This means that when a wavelet gets shifted in time, it generates different uh, coefficients in both time and frequency shifts. Second disadvantage is that wavelet transform has poor directionality. This means that wavelets only work the best on few angles like horizontal, vertical, and uh, diagonal. Uh, In processing 3D images, Wavelet transform struggles. It struggles to capture features like edges and represent features like textures of the images. So now I hope you gain good knowledge after watching the video, and you can see the similarities and dissimilarities between Fourier transform and wavelet transform. You must have also gotten to know that where you can use wavelet transform and where you can use Fourier transform, and which will be better in which case. By this, I'm going to end the video. Thank you.